All right, this is Honors Algebra 2 Pre-Calculus. We're doing Chapter 9 in Pre-Calc. Specifically, this is Section 9.4, which is Mathematical Induction. It's my personal favorite in Chapter 9, but I get that it's everybody else's least favorite. So, when you were in geometry class, you learned how to do two-column proofs, right? So you would make a statement, and then you would, in the other column, explain why your statement was valid, right? So like A equals B, and then you would say A equals B, or angle J equals angle Q, and the reason is they're alternate interior angles or whatever, right? So you would have a statement, and then you'd have a reason your statement works. So this is not a two-column proof, but mathematical induction is a method of completing proofs that is much more common in higher level math. So let's walk through the basic principles of mathematical induction, which are on page 645 of your textbook. And then once we walk through it, I'm going to show you lots and lots of examples to show you how it works, right? So here's the basic idea of mathematical induction. So let P sub n, right, Pn or P sub n, be some statement involving a positive integer n, right? So P sub n or Pn is the thing we're trying to prove, right? If P sub 1, meaning plugging in n as 1 as an integer, is true, and if the truth of some P sub k, wherever k is, implies that the next term, P sub k plus 1, is also true, then we can conclude that P sub n is true for all n values greater than or equal to 1. So let me kind of explain the logic of that, okay? So let's say that I know that P sub 1 is true, right? That's the first statement they said, if that's true. Okay, so let's say P sub 1 is true. Now, if I'm able to show that if some P sub k is true, then P sub k plus 1 is also true. Well, since P sub 1 was true, then P sub 1 plus 1, which would be P sub 2, must also be true by this statement, right? If P sub 1 was true, then P sub 1 plus 1 should be true. Well, if P sub 2 is true, then P sub 2 plus 1, which would be P sub 3, must also be true. And if P sub 3 is true, then P sub 3 plus 1, which is P sub 4, must also be true ad infinitum, right? Like on into infinity, all the way up. Like P sub, all the P's have to be true, because if I was able to show that the first statement was true, and if I'm able to show that assuming this works, this statement also works, I can then use that chain reaction to show that for all P sub n's, this statement has to be true. And I know that seems a little bit complex, but what this is going to boil down to essentially is a couple-step process that really addresses these two statements. And I'm going to walk you through the steps that you would need to do a proof by induction, and we're just going to do a bunch of practice at them. So basically, what these two steps boil down to, so when we do a proof by induction, right, it's really going to boil down to a couple things, okay? So when we do a proof by induction, right, so proof by induction, which is different than any other proofs that you've done before, okay? First thing, we're going to show that P sub 1 is true. Now, in a couple rare instances, they're going to say for n values like greater than or equal to 3, and then you would show like whatever the lowest case is. So P sub 3, if they said for n greater than or equal to 3. Usually it's for n greater than or equal to 1, so it's usually P sub 1. The second thing we're going to do is we're going to assume, and we're actually going to write this, we're going to assume that P sub k is true, okay? Then what we're going to do is we're going to show that P sub k plus 1 is true. And those are the three steps I need to take. So that's it, right? If I can show that P sub 1 is true, if I write that I'm assuming P sub k is true, and then I'm going to show that P sub k plus 1 is true, and as a hint, I'm going to have to use the P sub k formula. And I'm going to show you what I mean by that, but that thing that we assume to be true, I'm going to have to use that, okay? So we're going to walk through a really basic proof by induction. Okay, so let me pick a nice, easy one to start. Okay, so I want to show that, so we're going to walk through those three steps. So for my example 1, okay, I'm going to show that, let's do the sum of the numbers from n is 1, we won't use n, we use from 1 to n, right, of 2i minus 1 is equal to n squared. Okay, so So let me show you what I mean by that, right? So what that's saying is that if you were to plug in these values, right, we've seen sigma notation before. So if I were to plug in the I is 1 value, I'd get 2 minus 1, which is a 1, right? And if I plugged in I is 2, right, I'd get 4 minus 1, which is a 3, so that's my next term. And if I plugged in I is, so we can even call this S sub n, right, the sum of all these terms, right? If I plugged in I is 3, I'd get 6 minus 1, which is 5. So it becomes clear pretty fast that what's essentially happening is I'm getting all the odd terms, right? Up to 2n minus 1. Okay, so I want to show that this statement works for when I only use the first term. Okay, so the first rule is I want to show, in this case it's not p, it's s sub n, right? So I want to show that s sub 1 works. Well, that means literally just the sum of the one term, right? So that would just be 1. It's not 1 plus anything else, right? On the other side, the question is I'm showing does it equal 1 squared, right? So s sub 1, let me show you the logic here. S sub 1 is literally just the sum of the only term I have. The question is, does that also equal n squared? Well, it does. 1 equals 1, so check, S sub 1 works, right? The second thing I want to do is I want to assume that this works for up through S sub k, right, through the k term. Now, what that would mean, right, so I'm going to assume that this is true. So what I'm doing here is I'm saying that if I add 1 plus 3 plus all the way up until I get to 2k minus 1, that sum is apparently a k squared, right? That's a fact. So that's what I'm doing. I'm assuming that's true, okay? Because that would be what happens. Essentially, all I'm doing is I'm plugging in n equals k, right? So anywhere there was an n in this original expression, right, this whole thing, right, that this thing was equal to n squared, anywhere there was an n in this original thing, this is the thing I'm trying to prove. That's not how you spell prove. Okay, I would plug that in as a k and say, cool, that is a fact. Then using that fact, what I want to do is I want to show that the p sub k plus 1th term, it's not p, it's s in this problem, that s sub k plus 1 is true. Okay, so my job is to show that's true. So what I'm going to do is I'm going to erase up at the top so you can see a little bit better. And again, we're going to walk through a lot of examples of this, but let's talk about what this showing this thing to be true would look like, okay? So I want to show that s sub k plus 1 is equal to a k plus 1 quantity squared, right? If I can show that, I've shown that 1 works. I said that if I assume that s sub k works, I now need to show that s sub k plus 1 works. So let's figure out what s sub k plus 1 would look like. Well, it would look like a 1 plus a 3 plus a 5, all the numbers, right? All the odd numbers, right? Up to the kth term, which was 2k minus 1, right? That was when I plugged in k, right? Plus the next term, which would be when I plug in a k plus 1. So instead of k, it's a k plus 1. So it'd be 2k plus 1 in parentheses minus a 1. That's the k plus 1th term, right? And I want to show, question mark, that equals a k plus 1 quantity squared. Because instead of a k squared, I'm plugging in k plus 1. Sorry, I'll inch over for you, okay? Well, the trick to this, and the trick to almost every mathematical induction problem, is that we already know the value of all of this stuff. Because this was my s sub k term. I'm allowed to assume that all of this is a k squared because that was the assumption we made in step 2, right? We assumed in step 2 that I could say that 1 plus 3 plus 5 all the way up to 2k minus 1, the kth term should be k squared, and then I'm allowed to assume that's a fact. So now I have that it's that plus this one term that I wasn't able to include because it's the k plus 1th term, which if I clean up is a 2k plus 2 minus 1. And I'm trying to show, question mark, that equals k plus 1 squared. Now, because this is a proof, I can't add and subtract things to both sides, so I need to make my left-hand side look like my right-hand side. So if I keep going, I'm going to get that this is a k squared plus 2k plus 1, and I'm trying to show that it equals a k plus 1 squared. Well, this is a perfect square trinomial. It factors into a k plus 1 times a k plus 1, or you could write that as a k plus 1 quantity squared. They are exactly the same, so since I assumed that 1 worked, and I showed that if some arbitrary term k works, then every term after k, then the next term after k works. So by mathematical induction, s sub n is equal to that n squared, right? Like the thing they wanted me to show is true.